This example is 5B, so it goes with the previous problem. When the question says find the value using bond energies, it's the same, different approach, but the same value that we found before. So the value for delta H, not of this reaction. You'll notice it's the same reaction with the C6H6 that we had before. Our approach, however, instead of using standard heats of formation, we're going to use bond energy values. So the very first step you need to do is draw out your Lewis structures. I would not expect you at this point in the game to know the Lewis structure for C6H6. That's a common organic compound called benzene. You can see it has alternating single and double carbon-to-carbon bonds, and those 6 carbons are in a ring. However, the other ones that you see here, like O2 or the carbon dioxide or the water, those are easy enough that I think you probably have those memorized. If not, you should. So I minimized the Lewis structures and I brought up this table of bond energies, which you would always have access to. Your single bonds are at the top and then multiple bonds are at the bottom. So for example, a carbon-carbon single bond, 1 mole of them would take 346 kilojoules to break. If you have carbon-carbon double bonds, that would be 610 kilojoules for a mole of those. And for a mole of carbon-carbon triple bonds, it would be 835. So you can see that the greater the bond order, the number of bonds between 2 atoms, the larger the bond energy, the more energy it's going to take to break it. One other thing that you'll have to add in here is an exception. So even though it's simply a C-double-O bond, the ones in carbon dioxide are particularly strong. So instead of taking, I should actually move this down here. Instead of taking 745 kilojoules to break a C-double-O bond, in carbon dioxide, it's actually more like 799. The 745, even though it's an average, is not a very accurate one. So anytime you're looking at carbon dioxide, you'll want to use the 799 number. The equation that you're going to use is delta H of the reaction is equal to the sum of the bond energies for the reactants minus the sum of the bond energies for the products. Now, we just got done stressing that in chemistry, it's always final minus initial. Yeah, well, here's an exception. Instead of doing products minus reactants, which is what you do for standard heats of formation, T final minus T initial in a calorimetry problem, here's the one time you're going to do reactants minus products. And it has to do with the definition of bond energy. By definition, bond energies are positive. They're endothermic. It's the amount of energy it takes to break 1 mole of a certain type of bond. But products, you're not actually breaking the bonds. So we pretend we're breaking the bonds here to use bond energy values. But what's actually happening is the bonds are forming. So that's an exothermic process. So they'd be releasing heat. So that release is kind of inherent in that minus sign, in the subtraction sign. So that's why this formula works. If you have any questions on that, just make sure you ask in class. But here's the one time you really have to remember, it's reactants minus products. Now we're ready to start our problem. We're going to have 2 different columns, reactants and products, and then within those columns, we have to list all the bonds that we can see from the Lewis structures for our reactants. So there's a carbon-to-carbon single bond. We have carbon-to-carbon double bonds. We have carbon to hydrogen single bonds, and we have oxygen to oxygen double bonds. So those are all the different types of bonds. Now we have to count the number of bonds. So do be careful. It's going to be the number in a single Lewis structure or a single molecule, but you also have to take into account the coefficients. Now here it's 1, so that's not a problem, but here it's 7.5, so that would be an issue that you need to account for. So our carbon-to-carbon single bonds, there's 3 of those, and we only have a 1 in front of the C6H6, so we're good there. Same thing with the carbon-to-carbon double. Carbon to hydrogen single, there are 6 of them. Now, oxygen to oxygen double bond, there's only 1 per molecule, but there are 7.5 molecules. So we have to have a 7.5 there. Okay, then to get the bond energy, that's what you're going to look up in on your chart. So for example, carbon to carbon single bond is 346. Okay, you're going to go ahead and look up all the other ones. And then what you would do is multiply the number of bonds by the bond energy. Okay, and then eventually we're going to sum all these up to get an answer on the reactant side. We're going to do the same thing on the product side, and then we can put it into our blue formula to get the delta H of the reaction. So I finished filling in the rest of the chart. Compare your chart and your arithmetic with mine. When I sum up these numbers in red, these products in red, I'm going to get 9,081 kilojoules. Okay, and that's going to go on my reactant side. Now what I have to do is a similar chart, but for the products. So my types of bonds on the product side are C to O double bond and H to O single bond. Now, my C to O double bond, I have 2 just within one Lewis structure or one molecule, and I have 6 of those molecules. So here we're actually going to multiply our bond energy by 12. And for the water, a similar situation, we have 2 per molecule, and then we have 3 moles of the molecule. So we're going to multiply by 6. For the bond energy for the C double bond to O, that is not going to be the 745. That's going to be the special situation, the 799. So we'll multiply those. And then the hydrogen to oxygen single bond is going to be 463. So I'm going to do my arithmetic. You can see I have the sum of the product bond energies now, and that's going to go right here. So once I take 9,081 and subtract from it 12,366, I'm going to get an answer here, which will be our delta H value for this reaction of negative 3,285 kilojoules. So you can see that it's exothermic, but you can also see if you go back to the previous problem, it doesn't match it perfectly. And that has to do with some of the assumptions that we talked about in class.